Hello everyone, welcome back to Let's Inbound. So yes, we are in ninth episode of this particular playlist. So in this series, we are actually reviewing the concept and solving problems of every sub-unit. So we are in second unit and 2.9 logarithmic expressions. So yes, after this, you will get logarithm-based functions and all stuff. So this is the basic. Pay attention, do watch the video from the beginning till the end, and also be ready with pen and paper if you have scientific calculator, so be ready with that, or you can use desk mouse also. Yes, so let's get into that. What is logarithms? Then logarithmic expressions. Okay, what is logarithms? Let's start with this. What is 5 power 2? Yes, I can hear your answers. It's 25. Then this is something, you know the base, you're raising something like 2 means, 5 times 5, it's 25. You know how to evaluate this. But now I have the base 2 and I know the answer. I want 32. How much power I should raise? What should be my exponent in this case? So what is my exponent? To answer this, we need logarithm. Okay, so yeah, actually you can try, like you will make the 32 as power of 2, but this is how the logarithm comes into the picture. So how we can write this? Your exponent form and logarithm form are interchangeable. So for this question, like I'm telling you, I have a base 2. To what power I should raise the base 2 so that I will get 32. So I was telling a lot of words. Verbally, it was kind of big. So in logarithm form, you can, whatever I said, in math form, it's how it is, log with base 2. And what do you want? 32. That's it. This answer box, the output is there, right? That is your, what power should I raise the 2? Okay. So this is how we will write the logarithm form. And yes, this is the intro of logarithms. Here, exponent form into logarithm form. If your exponent form is a power x equal to a y, then your log form is, when you see exponent has base a, in logarithm form also log will also have a base. So log with base a, and input and output got exchanged. Here, this is output, the result, but the result becomes input, the input becomes the result. That's the thing. Okay, copy the base, then exchange the input output. That is, but here we have a condition for a. Your a should be greater than 0, and your a cannot be 1 also. Then, and whatever you give input of log should be positive. Okay, so these are the conditions for base greater than 0, but 1 comes greater than 0, or it should not be 1. These are the two conditions, and y will be always positive, not even 0. Right, so now linear scale versus logarithmic scale. So what is linear scale? To represent a temperature like this, we will use linear scale. Equal spacing on the axis means equal differences in values like 2, 4, 6, 8, 10, 20, something additive values will be there. Example, a simple ruler, same amount of values we will add up. So this is best for data that grows additively. And of course, the linear growth. Now, logarithmic scale is where we can use it. Here, equal spacing on axis means equal ratios in value. So it's not like 10, 20, 30. It will go like 10 and multiplied by that 10, 10 square, 10 cube, 10 power 4, or 2, 2 square, 2 cube, 2. So whatever your base, you can pick. But logarithm have base conditions. We have to rely on that. Now, best for data that grows exponentially. Yes, multiplicative changes means so if a sequence like goes by multiplying something throughout, that is exponential growth, right? So this is best for data that grows exponentially. And yes, these exponents and logarithms are super related to each other. We will see that. So this is logarithmic scales. Basically, we'll start from 10 power 0. That is called common logarithm. Why I'm always picking the 10? This is called common logarithm. And I will tell you about different logarithms after this. So now, logarithmic expression. Okay, so actually this is y equal to log 10 with something x, but it represents a line. You should carefully check this. Your x-axis is logarithmic scale. For y-axis, they use linear scale. That's why we are getting a line kind of figure. Otherwise, it will be a curve if it's both linear and linear. Okay, so that is how we will do when we come to logarithmic function. So it will be something like this, like a kind of this, when it's both linear and linear. Okay, coming to this, on a richer scale of earthquake magnitudes, a magnitude 5 earthquake is 10 times more powerful than magnitude 4. So why? Because if it's 10 power 4, 10 power 5, it's 10 times the relation, right? If your magnitude is 5 and another magnitude is 4, it's not one time difference. So here we will do times difference. It's not about subtracting, right? So that is, the scale is logarithmic. So each step represents a tenfold. It doesn't mean, oh, it's line. So it is additive increase. No. We should check on the scale. It's a multiplicative increase. Okay, this is how, like dealing with measuring earthquake, the most common scale, seismic waves, look, these things will work here, right? Okay, so now law of logarithm, this will be helpful when simplifying expression and condensing an expression, like very big expression will be there, we will make it some like single log, something like that. So we have learned exponent class, right? A power m into a power n equal to a power m plus n. It's very similar to that. Log with a base b and mn is a product. Okay, so single log, if you want to expand it, log with the same base b m plus log b n. So if it's single log in division, like your input is in division, you can expand the log. You distribute the log, but it's subtraction. And this is one important log m b log b m power k. So this k can be put in front of that. So k log b m, and log b 1 is 0. So if your input is 1, no matter what base, like valid base, your output is 0. And base and input matches means it's 1. No matter what, log 10, 10, log 4, 4. Okay, so these are laws of logarithms that will be helpful. Now, one more law of logarithm, this is called change of the base rule. So in our calculator, we will have like common logarithm, which is represented by log. Common logarithm is simply log, and it means actually log with base 10. This is common. There is one more logarithm called ln. This is called natural logarithm. We are writing it specially because it's log with base e. What does e means? E is a special Euler number, approximately 2.7. Okay. So these are the things. And for other bases, we should mention. So if you didn't mention, it means you're they are coming 10. If they mention ln, okay, they are trying to say the base is e. If any other bases, we should mention. So log root 2. So these bases have to be mentioned. Okay. So that's why log 10 is a common logarithm. Mostly simply log is enough. Okay. So now log bm, this is change of base. B is something root 2. You won't find it in your calculator, scientific calculator. Okay. So what can I do? I want to solve with calculator. Log root 2 5, something I got. So in this case, your calculator only have log 10 means. So yeah, you can change the base as you want. You don't want root 2, so make it log 10. Or if your calculator have log 5, so whatever is available, you can do. So let me make log 10. Then what should I do? Your input at the top, then log 10. Whatever you choose the base, that is the that you can choose. Log 10 root. Now you will have this in calculator, you can divide them. Okay, and then log ms, here they have changed it to natural logarithm. Yes, you can change the base. They pick base e. So log with the base that you have chosen, and input will come in the numerator, and log with the base you choose. Then log BMS. So this is converting to common log. Actually, one single rule. I have just the differences here. Okay, change of base rule works like this. Now we are into the question part. Evaluate the logarithms log 64 log e power 4 without using calculator. So let's start one by one. Okay, exponent forms will help us here because we know how to write exponent to log, log to exponent. So first write a question. Log with base 64 4. So what does it mean? 64 will be raised to a number, let it be x, and your result will be 64. The input will go to the output. Output means after equal. And the exponent will be the question whenever you solve the log. Okay, how will you solve it? Let's make same denominator, same base, because here 4. 64 we can write 4 cube whole power x equal 4. 4 power 3x power to the power rule equal 4 power 1. So two things are equal, like two exponent forms are equal, their base is same as their exponents would be same. So 3x equal to 1, x is 1/3. And this is our final answer. 1/3. Right? And next, this is the easiest one. But let me explain this. ln e power 4. Okay. What is the base of ln e? E power something will give you, this is your input. Okay, your input is e power 4. Super easy. So e power x equal to e power 4 means x is equal to 4. You just take with the exponent. Okay, that is something called ln and e, or natural ln and like Euler number or inverse. So they will get cancelled. Your 4 will be answered. Something like this also we can do, but it's not an official one. But we will solve sometimes like that. Okay, moving to C. Log with base 8, 1. 8 power something gives you 1. What is that? Let's make base 8 on both sides. 1 can be written as 8 power 0. So x is equal to 1. We also seen this in standard, sorry, x is equal to 0. We have also seen this log, whatever your base, if your input is 1, it's going to be 0. Okay. So now the last part, D. Log 0.0001. So what is the base? If no base is mentioned, it means log with base 10. So log 10, 0.0001. Okay, 10 power something is 0.0001. Right side you can express in power of 10, right? After decimal you have 4 places, so 10 power negative 4. Here 10 power x. X is negative 4. That's it. So this is equal to negative 4. Right? And this is how we will evaluate logarithms without calculator. You can try this with calculator also. It's kind of simple. Now, moving to question number 2. For the given data, construct a plot using logarithmic scale of base 10 using given values. Be sure to label your axis. Okay, so actually we will represent, we can represent this like this. Okay, logarithmic scale like your Mars, Europa, something like this. This way also we can do. And one more way is like just taking a 1D scale, something like this. But how can I plot? These are like normal numbers. For logarithmic scale, we should do something different. Let me show you. First, you have to do the log computation. Very simple. What base they are insisting us to do? Logarithmic scale of base 10. So you just, these are your inputs. So you just do log 10, 10. Log 10 means like just log is enough. You just find all the values using calculator, and I will show you how to do it with Desmos. Okay, so now let's do Desmos now. Here we go. So very simple. You just give log with base 10. So you can give log base 10 and some a and add a slider for a. You can give values whatever you want. Okay. Otherwise, you can give just log a also you can give. Okay, just and I'm adding this. Let's see. So log first is 10. See, you got 1. Without the base 10 I give, right? This time also it will give the same answer. So log 10 is 1. 10. Like if you mention the base or you didn't mention the base, this is how it will work, the common logarithm. So I'm doing this. Then I want what is log? Okay, my second data is 450. So in place of A, in place of 10, it's 450. So I got this. Okay, let me do this. First I got 1. Then we got 2 point. Let me make it to 1 decimal place, 2.7. Then I'm just referring the values of 50,000 as the next data. So I got 4.69. So when you make it to 1 decimal place, it's 4.7. And this way you can do it. Then log, okay, 1,200,000. Yep. 6.07 means we can make it 6.1. And the last data is 80 millions. That's a great thing. 80 million. It gives me 7.9, approximating 10 places. So I will be using this in my table, and then we will plot the logarithmic scale. So here we go. Okay. So these are the values that we, this is 1, 2.7, 4.7, 6.1, 7.9. And we will be plotting this in a 1D, like a one-dimensional line. Okay, let's plot it. So how to name the scale? So they said base 10, right? You should start from base 0, like base 10, power 0, 10 power 0, 10 power 1, 10 power 2, 10 power 3, 10 power 4, 5, like we need till 8. So, sorry, 6, 7, 8, 9. And let's go 10 power 1. Exactly, I got 1. So you should mark that. So what it is Mars. Okay, so you can mention Mars. Next one. 2.7 means this is 2 and 7. So we are just looking the powers. 2.7 means 2 between 2 and 3. It's very close to 3. So here is your second planet. I think it's Europa. Okay, so I'm just mentioning EU. And then 4.7 will be here. This is planet Titan, so shape T. And 6.1 is close to 6, 10 power 6. And that is the planet Enceladus. Okay, EN. And last one, 7.9, it's somewhere closer to 8, like 10 power 8. And it's our Earth. Right? That's simple. This is how we will represent logarithmic scales. It's easy to compare how many times one planet have the bacteria count of one planet than the other. This case, this will help us, like logarithmic scale will help us. Okay. Now, last question, condense the expressions A and B and expand the expression C. Okay, so this is expanded. We will make it simpler. The last one is single log. We will make it bigger, like we will expand that. So let's solve one by one. Minus 5 log x plus 1 plus 3 log to 6x. So first of all, when you're simplifying, make sure before your log, there is no number sign, negative or anything. So we will be focusing on this. What rule? We have the rule log with any base, m power n means you can write n log am. So now I have n means, then I can take it to the power. If you have it to the power, you can bring it. So I can take it to the power of the input. So log 2 x plus 1 whole power negative 5. Then plus log 2, 6x is your input. So whole power, this 3 will go to the power. This is the first step. Next, this rule. Log A, I have an input, plus log the same base, I have another input. How can you condense this? So simplifying means making single log. So put the same log with same base, and you should, if they are added, you should multiply mn. Okay, so that's the next. So log 2, I should multiply x plus 1 whole power negative 5 into 6x the whole cubed. And we can simplify the input log 2. 6 cube is 216. X cube is x cube. And x plus 1 the whole power minus 5, you can take it like if you want. We want to make it positive exponent. So that will convert to denominator. This is the simplest form. Log 2, 216x cube by x plus 1 whole power 5. Okay. So that's the thing. Now, question number 3. Again, before log, if you see something, first work on it. So log 4, 10 power 1/3 plus log 4, h power 1/3 minus log, don't take the minus here. Okay, this is an operation subtraction. Log 4, g power 6. Now everything have log. First, let me condense this. So log 4, they are added, right? So their inputs will get multiplied. 10 power 1/3, h power 1/3 minus log 4, g power 6. Next is log 4. I'm going to simplify 10h whole power 1/3 I can write, correct? Minus log 4, g power 6. Now same base, but they are subtracted means put the log with the same base and divide them. 10h whole power 1/3, g power 6. I'm going to simplify it further. So log 4. What is power 1/3 means? That is cube root. So cube root, under the cube root you mentioned 10h and then g power 6. Got it? Next, last part, expanding a log, single log to expansion. So the reverse way of using the rule, here you don't do this, like don't take 8 power, so let it be here itself. Okay. When you are simplifying only, we will check there is no number in before the log. So let it be 8 as it is. And log 4, two things are divided. Like this is your m, this is your n. So m by n means what? Log 4 x z power 6 minus log 4 root y. Okay, equal to 8. You can simplify it further. Like this is now in product. Log 4, that is a product. Yeah, I can expand it. So log 4x plus log 4 6, z power 6. Okay. Then minus log 4, I'm going to write it y as y power half. And 8 log 4x plus log, okay, you can bring the 6 before, right? So 6 log 4 z minus, here also do the same, half log 4y. Then you take the 8 inside, 8 log 4x plus 48 log 4z minus 8 into half is 4 log 4y. This is the expanding single log into this. So when you work on the condensation of this, you will get back this. Okay. And this is how the rules have to be applied in logarithmic expressions. And yes, I have a bonus question on expanding. Okay. So expand the logarithmic expression. You can take a screenshot of this. And that's it for today's episode. I will be meeting you in the next video very soon. Until then, keep learning. And yes, here is a reminder. There is a community for students by Let's Unbound. So you can join that by scanning this so that you will get future updates of our courses and webinars. So that's it for today. Keep learning, keep practicing, stay curious.